Okay, we have discussed that a random process is basically an ensemble of different functions, functions of time. Okay, this is what is a random process. So you have x t, zeta 1, then x of t, zeta 2, and so on. Okay, this is what is called as the ensemble of the random process, the set of all the possible outcomes. Okay. Like I have said that if I record a speech for 10 seconds and I repeat this experiment again and again, so you can expect that every time I record the speech signal, its outcome is going to be different. Okay? Sorry. So unless and until you basically perform this experiment, you cannot predict what type of outcome is going to occur. That is what is a random process. Okay? So to characterize a random process, if you see at any particular time, maybe t1, this I take a time t naught or t1. At t1, if you take the samples of the sample functions, the values of the sample functions, this basically generates a random variable. Okay. Similarly, at some other time t2, these values of the sample functions at t2, it gives you another random variable. I can say this is x1, this is x2, okay, or xt1 and xt2, t1 and t2. So your random process in which we have a collection of different signals which are a function of time, and at any particular time instant, maybe t1, if you take the amplitudes of all these sample functions at particular time t1, that becomes a random variable. Okay. Similarly, at any other particular instant of time t2, if you find the amplitude of all the sample functions, that gives you another random variable, and so on. So at t3, you have another set of amplitudes. Okay. So this is another random variable. So the values of these sample functions at a particular time, that itself becomes a random variable. So random process in that case you can define as the time index sequence of random variables. Okay. So we have random variables that is a function of time. So at this time, the random variable takes these values. At next time instant, the random variable takes different values, and so on. Okay. So to describe this entire random process, either you can describe it mathematically or analytically. Like suppose if I say I have a random process defined by xt is equal to a cos of omega ct plus theta, capital theta, and if you keep a and omega c fixed, that is amplitude and the frequency is fixed, and if theta, which is the phase, if it is allowed to vary between 0 and 2 pi, then definitely you will have a set of different waveforms. Okay, so if I suppose say this is t and this is 0 at t is equal to 0, so if you take theta as 0, then it is simply cos omega t ct, and in that case at t is equal to 0 you will get maximum value, that is a. So you will have a waveform like this. Frequency is omega c and the amplitude is a. If you change this theta to maybe pi by 4, then at t is equal to 0, you will not have the amplitude as a, amplitude will be a cos of pi by 4. Okay, so that will be less than a. Accordingly, there is a phase shift, and you will have a different waveform, maybe like this. Okay, and as you go on changing this theta, you will get different sort of waveforms. Okay, of course, the frequency of all the waveforms is same, and the amplitude is also same, but I'm changing the phase. Okay, so that can be one way how we describe a random process. Means you can have a mathematical relationship for this or analytical relationship, right? But that is generally not available for the practical situations. What you do in the practical scenarios is that you obtain an ensemble of the random process. Okay, instead of describing it analytically, because you don't have a model, so you just obtain an ensemble experimentally. It means you basically have different measurements of the same process, and then you get a collection of signals which we call as ensemble. Okay, now from this ensemble we can characterize the random process. Okay, and we have already discussed that in this ensemble at a particular time instant t1, the amplitude of the sample functions that constitutes a random variable. Okay, like at another time instant, maybe t2, the amplitude of the sample functions at this instance it constitutes another random variable, and so on. Okay, so at t1 you have some values here. Let us suppose I define this random variable x1. This is a random variable x2. Okay, so the values which the sample functions take at t1, I call it as a random variable x1. The amplitude values which the random variable takes at time instant t2, I call it as a random variable x2, and so on. So you may have n such observations. Okay, you have different observations, and these observations are measured at n different time intervals. Definitely, you will have n different random variables x1 to xn. Okay, and generally these random variables they are dependent in nature. Okay, so for these n random variables, you know that if you have one random variable, then it is described by its PDF, the probability density function. Okay, px of x. When you have two random variables, then it is described by their joint PDF, that is pxy of xy. Okay, and we already discussed these random variables now. So if px of x is the PDF of the random variable, it is continuous random variable, definitely, then x pdx, it gives the probability of finding the random variable x between x and x plus dx. Okay. Similarly, px of xy, this is the joint PDF of two random variables x and y, and if you multiply this with dx dy, that will give you the probability of finding the joint random variable between x plus dx and y plus dy, and so on. Okay, or you can also characterize in terms of this CDF, like we have fx of x, and you have here fxy of xy, that is the probability of x less than equal to x and probability of y less or equal to y. Okay, and this can also be taken as the integral of this derivative of this function, and so on. So if you take if you have a ensemble, and from this ensemble, if you generate n different random variables, which are nothing but the amplitudes of the sample function at different time intervals, okay. Then for these n different random variables, they can be fully characterized by n order. We can have a n order joint PDF or CDF. Okay, if you have CDF, then you have fx of x1, comma x2 up to xn, t1, t2 up to tn. That will be given by the probability of xt less or equal to x1, comma xt less or equal to x2, and so on up to x of tn less or equal to xn. This will be the joint PDF. Okay, this will be the joint PDF of these n random variables. And if you find it, this is a joint PDF, and if you find the joint PDF of n random variables, you will have px of x1, x2, xn at t1, t2 up to tn. That will be the partial derivative dn upon dx dy up to dx1, dx2 up to d of xn of the CDF fx, x1, x2 up to xn, t1, t2 up to tn. So if you have this joint CDF or the joint PDF of the n random variables that you have extracted from this random process, this will completely specify, okay, all the statistical parameters about this random process. Okay, so like suppose if I take the second order, means you just take two samples, maybe at t1 and at t2, so you get a random variable x and a random variable x1 and random variable x2. Then in this case you will have fx of x1, x2, comma t1, t2. This relation will become, this is the CDF x1, x2. That is the joint CDF of random variable x1 and x2, which are basically obtained at time interval t1 and t2 respectively, is the probability of xt less or equal to x1 and probability of xt less or equal to x2. Okay, and likewise you can have this joint PDF, that is d2 upon dx1 dx2 into its CDF. Okay, so if you know the PDF, the joint PDF or the joint CDF of any random process, then you can fully characterize it. Okay. But generally, the two important statistical parameters that are used in the measurement is, one is the mean and one is the autocorrelation of the random process. If you find the mean of the random process xt, that will be given as integration of x into px of x t into dx. Now if you see here, this mean is basically a function of time. Okay, and the probability density function is also a function of time. Okay, otherwise if you just have one random variable, so for a random variable x we take its mean value as integration of x into px of x dx, because there is no time dependence. Okay, but in case it is a random process, then it is a time indexed sequence of random variables. Okay, so we have random variables indexed with time. Definitely the mean is a function of time, and its probability density function is also a function of time. Okay, what it actually means is that, suppose if I take a random process, so you have an ensemble which is a collection of different possible outcomes. Okay, so at any particular time t, these sample values, they give a random variable, and for this particular time t, if you find the PDF of this random variable, that is what is basically px of t. Okay, and if I change this time t at another time, suppose t naught, at another time you have another random variable, and for this random variable you will have another probability density function. Okay, these are the individual periods, not the joint periods. Okay, so at particular time instant you will have one PDF, and as you change time t, the random variables will be different. Accordingly, its PDF will be different. So the mean at this time t naught, if I take a particular value t naught in this case, so that will be x of x bar t naught is integration of x into px of x at t naught dx. So what I need to find is that for this particular time, at this particular time t naught, I have a random variable, and if I know its probability density function, I can find its mean. Okay, so it is the mean of these points at this time. Similarly, the mean of these points at this time, and so on. Okay, so px is not, in this case, you can say independent of t. It is basically a function of t, because every time instant you take the samples, the random variable is going to be different. Okay, and as a result, its PDF will also be different. And if its PDF is different, definitely all its statistical parameters, its mean, its variance, mean square value, everything will be different. Okay, so in general, in a random process, as you go along the time axis, as you go through the time, the mean of the random process varies. Okay, it is a function of time because its PDF is a function of time. Now, depending upon, if suppose I have finite number of samples, I have finite number of samples in this random process, then definitely these samples will take some finite value. Okay, and you can plot its PDF for this particular time, and then multiply those PDFs, then multiply that PDF with the values which the function can take and integrate, you get its mean value. Or if it is discrete, then in that case it is simply summation of xi into probability of xi. So if suppose this random variable takes some discrete values, which is not continuous function. Okay, here we assume that the random variable takes a continuous range of values. If I assume that the random variables, these points, they take some discrete set of values, then you can multiply this with its CDF and summation over I, you will get its mean value for this time. Okay, and the second important parameter is, and one you can say that if the PDF, suppose if the PDF of the random process is not available, okay, because to compute the mean of the random process in this way, you must ensure that you have the PDF of this random process at each and every instant of time. Then only you can find the time very mean along the process. Okay, if the mean, if the PDF of the random process is not estimated or if it is unknown, then instead of using the statistical averages, you can use ensemble averages. And ensemble averages, what I simply do is that suppose I'm getting rid of this PDF, the probability density function. Okay. So at this time, suppose you have 100 samples here, 100 set of functions. So at particular time, definitely you will have 100 samples. Okay. Then the mean value at T naught is simply the sum of all these 100 amplitudes divided by 100, and so on. So in general, if we have m samples functions of the random process, then the mean of the random process at a particular time T naught will be given by, I can take it as summation of xk of T naught, where k is from 1 to n, and divided by m, and the limit, of course, m goes to infinity. So this is what is the actual way to compute the mean of the random process. Okay. So you have a collection of functions, and this is what is the random process. So at a particular time T naught, what I do is that I find the sum of all the amplitudes. So this is, I say, x1 t, this is another function x2t, x3t, and up to x of mt. So x1 at t naught, x2 at t naught, the amplitude of this at t naught, x3 at t naught, and so on up to x of m at t naught divided by m. That will give me the mean value of this random process at time t naught. Okay, so this is what we call as ensemble averages, and in fact the ensemble averages they can be used to compute the mean if you don't exactly know what is the PDF of the random process at each particular time. Okay, and then we have another important statistical parameter which we call as the autocorrelation function. Autocorrelation. In fact, mean is not that important, because if you have any random process, you can always create a zero mean in the process by subtracting the mean from the random process itself. Okay. Autocorrelation is a very important parameter for the random process, because we will see later that the autocorrelation and the power spectral density, they form a Fourier transform pair. Okay. It means if you want to find the spectrum or the power spectrum density of any random signal, you can just find its autocorrelation and take its Fourier transform. That's it. Okay. Now, how you define the autocorrelation? If you find suppose the, in fact, it is a special case of cross correlation. Okay. So cross correlation or correlation between two random variables is defined as expected value of xy, or it is xy bar, any notation you can use. So if I have two random variables x and y, and if I find the expected value of xy, we call it as cross correlation. Okay. So, or what you can write it as rx1 t1 comma t2. In this case, for the random process, it is x1 x2 bar, and that I can write as double integral minus 2 plus infinity become x1 x2, then the joint PDF px1 of x1 comma x2 at t1 and t2 into dx1 dx2. See what this relation basically represents, that if I take two random variables x and y, and if I find the expected value of x and y, this is what I call it as correlation. The correlation between two. Okay, this already we have discussed in the covariance. So covariance of the two random variables is basically x y bar minus x bar y bar. This term we have called it as correlation. Okay. Now the random variables that you are generating in the random process, they are basically from the SAM process. So at some time t1, you have one random variable, which I say suppose it is x1, and then at another time instant t2, you have another random variable. Okay. So you are trying to find a correlation between these two. That is what is cross correlation. But since these two samples, they are coming from the SAM process. Okay. Both the random variables, they are being generated from the SAM random process, so we call it as the autocorrelation function instead of cross correlation. Okay. And this is the SAM equation like this. The only thing is that instead of using x, y bar, I am using x1, x2 bar, where x1 is the one random variable which you are getting from the random process at time t1, and x2 is another random variable which you are getting from the same random process at time t2. So if you find the expected value of x1, x2, that will give the autocorrelation of the random process at time t1 and t2. Now to find this autocorrelation, what you need to find is the joint PDF of the two random variables which are basically computed at t1 and t2. And this t1 and t2, definitely it can be anywhere on the time axis. Okay, like suppose this is t1, t2, or I can take this as t1 and this as t2. So this will generate one random variable and this will generate another random variable. Then definitely to find the autocorrelation, what I need to find is I should have the joint PDF of these two random variables which are generated at time interval t1 and t2. Okay, this is what is again the statistical average. But you can again use the ensemble average, that if you have a set of random signals x1, x2, t up to x of mt, so you can get rid of this the PDF function using the time averages just like we have used in the mean. Okay. Then I can find that the autocorrelation between the two at time t and suppose t plus tau will be equal to, so if you have an ensemble of m signals, then this can be computed in a way that you multiply these two and find its average value. That is it. Okay. So suppose at t1 and at t2, I am finding the autocorrelation. So this sample will be multiplied with this sample. This sample is multiplied with this. This is multiplied with this. That gives you x1, x2, the multiplication term, and then you take its expected value, which is nothing but the average. Okay. So multiply the corresponding samples and find their average. That is how you can find the autocorrelation using sample averages. So I can write it as summation of xk of t into xk of t plus tau and k from 1 to m, 1 by m, limit m goes to infinity. So this is nothing but the product. Okay, so in case 1, you have x1t and x1t plus tau. So x1t is this, x1t plus tau is this sample. Then plus x2 of t and x2 of t plus tau. So this sample and this sample, they are multiplied. Okay, and finally you add it together and divide it by m. That gives you the average value. This is how exactly you find the autocorrelation of the random process. The PDF, the joint PDF information is not available. Okay.